Okay. Ta-da! Technology finally cooperated. Okay, so you just asked which questions will be on the quiz. And everybody probably wants to know that. And I'm going to say it today in class as long as I don't forget. So hopefully I won't forget. Please remind me if I forget in class. But it's homework 4, 1 through 9, which all should be pretty easy to do. And homework 4, 15 through 18. These are all titration problems. Those are all the titration problems. In between these two are some buffer problems that we might get to today. These will for sure be fair game. Okay, what other questions do we have? What problems have we been working on?
What about just like number 5 based on structures, which will be the stronger acid? Like I found them out, but I don't even.
Okay, so can you pass that to me? So we're looking at number 5. Oh, based on the structures. Okay, we actually don't have to draw these out to tell. So when we look at HIO versus HIO3, we can recognize that both of these are oxyacids, which means there's two things that matters for how acidic they are. We've got the number of oxygens, and remember that's the number of oxygens. It's not just straight the number of oxygens. It's the number of oxygens relative to the number of hydrogens. For this first one, because we've got the same number of hydrogens, we've got the same central atom. All that matters is the number of oxygens. Which one's stronger? This one?
More oxygen.
The one with more oxygens is more acidic. We can look at, so that's part A, and we can kind of do part B the same way. Part B is another pair of oxoacids, HOCl versus HOI. Now this is a little tricky, and I'm going to show why it's a little tricky. And that is part C, HCl versus HI. I always cut off the top a little bit. There we go. So we have to, the first thing whenever we're trying to assess the strength based on structure of an acid, the first thing we have to do is make sure we're in the right category, so we're getting the right dependence. The part B is oxoacids again. This time, same number of oxygens, same number of hydrogens. So all we care about is the electronegativity of the central atom. And the one that's more electronegative is going to be the stronger acid. Now, this is a smaller effect than the number of oxygens, but it's still an effect. And that's different than when we go here to our nonmetal hydride. In our oxoacids, we're always looking at an oxygen-hydrogen bond length, and so that bond length is the same for all of them. Since that bond length is the same for all of them, all we're caring about is the electronegativity. In counting the number of oxygens and looking at the central atom, we're just looking at the electronegativity. But when we go to nonmetal hydrides, we actually have a bond length difference and an electronegativity difference. So we're looking at the bond length and the electronegativity. And these are two competing ideas. Which one wins? You can check your nose too, but which one wins?
Bond length? I have, it says that mostly it's bond length that dictates how strong the acid is, but then below that I have electronegativity wins right to left, or bond strength wins top to bottom.
Yeah. So just which one wins is actually kind of a misleading question because it depends on where our comparisons are. If we're comparing two things side by side in the periodic table, the bond length changes very little, but the electronegativity changes a lot. So in that case where we're comparing across, bond length wins. Sorry, electronegativity wins. In the case when we're comparing in a single column, when we're comparing in a particular group, the electronegativity change is smaller, but the radius change is much larger. So bond length wins when we're going down a group. In this case, since we're looking at HCl versus HI, bond length is going to win. That means the longer bond is going to be the stronger acid, because the longer bond is going to be the weaker bond, which means the hydrogen in a positive charge will leave more easily.
How can you tell the bond length? Is that just something I've forgotten from 127?
Yeah, it's something you forgot from 127. Periodic trends. Do you remember the
I know it for
atomic radius trends?
Atomic radius and for electronegativity and for...
All you need to know is atomic radius. You have a periodic table handy?
I do.
So which has a bigger atomic radius?
Chlorine. What?
Chlorine versus iodine.
Yeah.
Bigger radius. No, bigger radius.
Yeah. Yeah.
Sorry.
Isn't... Because fluorine is the biggest.
Fluorine is the biggest electronegativity, but the smallest radius.
Okay.
Right? Okay, you had it backwards. Okay, good. I'm glad we sorted that out because that would have been a problem later on.
Yeah. Okay.
So, fluorine, top right corner of the periodic table, would be the highest electronegativity, smallest radius. That's part of why hydrofluoric acid ends up being a weak acid, barely weak. It turns out that even though it's got this really high electronegativity, the bonds are so short that they don't break apart that easily in water. Versus when you look at HCl or HI, you've got this decreased electronegativity, but you have this huge increase in radius, and that increase in radius makes it so the bonds break apart more easily. So HI would actually be the stronger acid in this case. Because this is a lot of definitions and concepts, no math. Are we good with that? Any other questions on the different types of acids?
So for part B, it would just kind of be the same thing where HOCl is the stronger acid?
Yeah, so HOCl is going to be the stronger acid because in part B, we're still looking at our oxo acid rules. And so it's going to be the electronegativity of the central atom that matters, right? Because the HO bonds are always going to be the same length.
Right, okay.
Other questions? More of you need to show up to office hours.
Can we do number 2 from homework 4?
Yeah. So that one that we just finished was number 5 from homework 4?
This next quiz is only over homework 4, yeah?
This next quiz is only homework 4. So number 2 from homework 4 has us calculate the Ka of lactic acid. So we're going to do lazy physical chemist way of talking about lactic acid. We're going to look at H-lac going to H3O plus LAC minus, and we've got an H2O over here that we're not too worried about. I'm going to do this in a really generic way because it turns out that I think the first 4 problems all pretty much do the same thing. We're looking at a Ka or a pH. We're usually looking for one of the two things, which means we're always going to be looking at concentration. We're always going to be looking at concentration because we'll always be doing an ice table. Yeah, so we'll set up an ice table. We can just say the initial concentration of lactic acid, I'll call it H black initial, 0, 0. We know that the equilibrium is going to be, well, that's a big negative sign, minus x plus x plus x. Whenever we're doing these initial concentration, initial pH acid problems, we always end up with the same fix that. We're always going to end up with the same kind of thing. We're always going to end up with this situation where we have Ka equal to H3O plus squared. Because of the 1-to-1 ratio, X is going to be that H3O plus. It's always going to end up squared, divided by H black. So essentially, we're always going to end up with, this is going to be at equilibrium, and this is going to be the initial. Notice we've made the X a small approximation. That's part of why we can just use the initial concentration of lactic acid. And we're also using the fact that it's a 1-to-1 mole ratio to use the H3O plus. And we're using the fact that we started with zeros for our reactants. But as long as all of that's true, we always end up with this situation where we've got 3 different variables. And you'll notice problem 1, problem 2, problem 3, and I think problem 4 are all, I give you 2 of the variables, solve for the 3rd. Right, so let's go ahead and look at number 2. Which variables are we given in number 2? Well, let's do the easy thing. What are we asked to solve for?
Ka and pKa.
Ka, pKa kind of mean the same thing. So if we're solving for Ka, that means someplace in the problem we have to be given the initial concentration of lactic acid, and we have to somehow be given the H3O plus concentration. I think we're just straight given the lactic acid concentration, right?
Yeah.
We're told it's great. And we're essentially almost directly given the pH. I mean, the H3O plus concentration. Are we given the pH?
Yeah.
What's the pH? What is it?
2.4.
2.43. I just heard the 0.43 and I was like, that doesn't seem right. So we can plug that all in and we can solve it. Now, the thing that becomes important, and I've mentioned this before, doing the math, right? Being able to read the problem and knowing what it's asking us to do and what pieces we have, what pieces we need, that's the skill that is most important. So when we see that we've got this, the H3O plus concentration can be given to us in a couple different ways. We can be given the pH. We can be given the percent dissociation. The percent dissociation would also give us the H3O plus concentration. And we can just be straight given the H3O plus concentration. There's 3 different ways we can be given this number. At this point, do you think you could solve it?
Yeah, so, but since you have the pH, you would just have to take the negative log of that?
Yeah.
Okay,
Yeah.
got it. All right.
So you just take the negative log, plug it in. Let's do that real quick and get a numerical value. You too, if you're watching at home. No one's watching.
I think if they are watching it live, I think it's more people referencing it afterwards.
Send an email to
True.
everybody.
I'm going to send an email.
Yeah, that's a good idea.
But you should all calculate. value do we get for Ka?
For K, I got 1.38 times 10 to the negative 4. But I'm not sure.
So, great, perfect, that's good. I mean, being not sure is okay. After we get this value, did other people get the same value?
Yeah.
So, after we get this value, we want to think, does this value make sense? First thing to consider, what do we usually see for our Ka values, right? We've been developing, we've been looking at different weak acids, we've been looking at different weak bases, we've been developing a little bit of familiarity and some intuition that goes along with Ka values. Do we see Ka values like this?
Yeah.
Yeah, right? It's similar to acetic acid, it's stronger than acetic acid. It's not as strong as some of the other acids, but it's a reasonable Ka value. It's not something absurd. We didn't get like 50 billion. We didn't get like 10 to the negative 34. We got something that seems reasonable. Here's another check we can do. Do you know what's the molecular formula for lactic acid?
C3H6O3.
If we put this into a structure, I have to remember what the structure of lactic acid is. If we put this into a structure, we can use our qualitative rules to say if it makes sense that we have an acid that's a bit stronger than acetic acid. We're all familiar with acetic acid. It's like boringly familiar with it. So if we looked at the structure, we've got a carbon, a carbon, a carbon with a carboxylic acid group on there. We've got an alcohol group, and then we've just got our hydrogens. When you look at this, and we could have looked, first off, you could have just looked up the Ka for lactic acid, and it's 1.4 times 10 to the minus 4. It's like, great, got it right. But also, we can use some logic. So if we look at this structure, we can say, okay, something similar to acetic acid. We've got a carboxylic group, but we've got an extra oxygen. For that reason, does it make sense that we've got something that's a bit stronger than acetic acid? Yeah. Yeah, we've got that extra electronegativity. We're going to have a little bit more of the electron cloud pulled away from this hydrogen, which is going to be the acidic proton. This hydrogen is probably never going to break off. Maybe in really extreme cases, but probably not in water. So yeah, it's a reasonable value. Cool. What other questions do we have?
Just really quick, it's also a question for the board, but just on number 15, it has a bunch of like more potassium hydroxide that you're adding, and this is like heavily paid for the following volume additions. Are these like adding upon each other, or
Total volume? Those are the total volumes each. Yeah, I hope it's supposed to be total volumes each. Yeah, total volumes.
We look great so far. Just going through, I calculated the initial pH for that one, and then just going through reaction to molarity. Then I'm going to do an ice table for that equation.
Yeah.
As well.
Yeah. So if you're looking at problem 15, if you're looking at homework 4, problem 15, it's a titration problem. And you're pretty much always going to do reaction to molarity, ice, pH. Hopefully you'll do this so much you get bored with it and you'll start to learn the shortcuts. Today in class, we're going to go over some of the shortcuts that we'll start to use. Particularly in the buffer region, we're going to use a shortcut called the Henderson-Hasselbalch equation. Initial pH, so this is the process for pretty much everything besides the initial pH. The initial pH is just like the problem we just did. And the rest is all reaction, convert to molarity, do an equilibrium table, calculate the pH. Over and over and over again, until we can start to do it in our sleep. Other questions? If you all just want to work for a bit, you can do that too. I don't know how to handle that with the. No, that's the frustrating thing. I can end it and start a new one.
I just had a quick question about number 18, because number 18 you said might be on the quiz.
Yeah.
It's a buffer question. Are we going to be going over that in class or like?
It's buffer-ish.
Buffer.
You should be able to do this. So I should admit, we technically already started doing buffer problems.
Okay.
Right? The example we did in class on Monday, we did a buffer problem calculation. I didn't call it that, but it turns out that the process on the board right now, that titration process, works in the buffer region as well. And also notice, let's instead of calling it a buffer, let me just ask you this. Can you calculate the pH if you have the Ka and the concentration of the weak acid and the concentration of the conjugate base?
I think so, yeah.
Yeah, right. So let's see how we set this up and see how we can actually already do it.
Yeah, could we do like letter A or for 8?
Yeah. Let's do A and B because
Okay.
A is not boring, but A is really important and almost too easy.
Okay.
So we're looking at a phosphoric acid buffer, which means we're looking at H2PO4 plus H2O going to HPO4 minus 2 minus plus H3O plus. And you can all get mad at me for not putting states of matter, but you know they're all aqueous. We're going to set up an ice table here. Initial change equilibrium. Our initial concentration of the H2PO4 for part A.
It's going to be 0.25 molarity.
And our initial concentration for the HPO4.
Also the same.
That's part of what makes this boring. So we can go ahead and say, oh, I've got a 0 in my products, which means I'm going to have to lose some reactants, create some products. That's going to give me approximately 0.25 molarity. Notice I'm using X as small approximation twice. I'm going to have the Ka equal to 0.25 divided by 0.25 times X. And again, I'm writing this the same way I wrote it in class on Monday. This is not how we usually write it, but I'm trying to write it to accentuate the fact that we've got a ratio of conjugate base to weak acid. That is the way that I'm writing it here, conjugate base to weak acid ratio, is going to be very important for the buffer calculations. What do you notice about this one?
Just 1x.
pKa equals pH. It turns out that this first point is actually a really important point. When we have half our moles in the H2PO4, the weak acid, and half our moles in the HPO4, we call this midpoint, right? I started out, you can imagine starting with all of your moles as the weak acid. This is when you're halfway to reacting all of your weak acid. This is the midpoint.
That's the middle of that buffer region, right?
Yes.
Not the equivalence.
Yes, this is the middle of the buffer region. And at the middle of the buffer region, pH equals pKa. That's going to be really important for this week's lab, the titration lab. You're going to determine the pKa by finding the pH at the midpoint. So that's really handy. If we go on and do part B, we're going to be not at the midpoint. We're going to be not at those concentrations. We're going to go ahead and switch to part B. What's the initial concentration for part B?
Yeah.
And, oh, they're both 0.75?
Yeah,
D is the one.
Oh,
Yeah, D has to.
that's boring.
So even if they're higher values, so let's say like we did B and there were 0.75, 0.75 would be the same answer, or because they're both half and half?
Yeah, so since since we've got concentrations of both present, right, we can go through the same process, minus x plus x. But since we've got the x's small approximation, we're still going to end up with approximately the same thing. We're still going to end up, we're still going to end up with Ka equals 0.75 divided by 0.75x.
And so if we do D where,
let's go ahead and set it.
Wait, can I just picture that real quick?
So part A, B, and C all come out the same,
okay.
right?
Okay.
They all come out the same. They have different total molarities, which is going to be something we talk about later. That's for the buffers lab. But because we're always going to this part that's the midpoint, we're always ending up with the same answer. If we go ahead and go to something that's interesting, we go to part D. Part D, what's the initial concentration of H2PO4?
175.
Oh no, it's not the same again, is it?
0.25.
Oh, 0.25, okay. And 0, we're gonna have our minus x plus x plus x. We're gonna go through the exact same thing again. We're gonna have 0.75, we're gonna have 0.25, and we're going to have x. Again, notice we're using the x's small approximation twice. We're assuming water's not contributing any H3O plus. We're using 3 different approximations in this. Hopefully all 3 are okay. We're going to get Ka is equal to 0.25 over 0.75 times x. Is problem 18 really that hard? No, it turns out buffers are really easy. Buffers are kind of easier than a lot of the other parts of the titration curve, because you're going to do this every time. We're in fact going to do this so much, we're going to recognize, I'm going to get ahead a little bit. We're going to recognize that x is H3O plus. So if I take the negative log of both sides, I can eventually get to this equation. Oh, let's make sure I don't mess it up. Okay, the negative log of that, add it over. That's the Hendron-Hasselbalch equation, right? You take the negative log of both sides, you get negative log of Ka gives you pKa. Negative log of x gives you pH. Negative log of the ratio is the negative log of the ratio. I add it to the other side. So I get pH equals pKa plus log of conjugate base over weak acid. Now you can kind of skip doing the entire ice table. If you've got your initial concentrations, you plug it in there and you're done.
How would you know if the approximations fail from that?
Ooh, yeah, right. So that's going to be the big problem. And we have this generic rule that we use for buffers to say if the approximation is good or not. We say as long as the pH is within plus or minus 1 of the pKa, approximations are pretty good. And that, now we're getting way ahead of class. We're not doing that till Friday. But that defines the buffer range, pKa plus or minus 1. It essentially says, look, if we want to use these shortcuts, we have to be someplace where the approximations work. So we're just going to limit ourselves into this buffer range where the approximations work, pKa plus or minus 1.
Jumping around, if we can go to like 15J, talking about what volume of titrant is needed to reach a pH of 3.22. Technically, you can mathematically set that up. I'm wondering if there's a simpler way to do this, or if the way I have it is correct. I mean, it's fine, but
sure.
Because right now I just have the K equals, I just chose Y rather than X because I didn't want to confuse with an X earlier. Y times the molarity divided by the, because volume divided by the initial volume plus Y times H2O plus, which I get from the pH 10 to the negative 3.22, divided by Y times the other molarity with that itself divided by an initial plus Y.
Yep,
okay.
That totally makes sense.
Sounds good.
Maybe not to everyone in the room or everyone watching, so let's go ahead and look at it on the board.
Maybe writing
But
it
it sounds like you've got the right setup. So essentially what we're doing is we're trying to do this type of calculation, right? except for now we're doing it backwards.
Yeah.
So let's do one that's forward, and then we'll see how we can switch to doing it backwards. Did you get an answer for part J?
I didn't actually go through with it yet. So
Did you do any of the calculations for 15
I
yet?
did D, which is 7.5 milliliters.
Were any of your pH calculations close to 3.22?
I got right up to getting the concentration H3 plus without doing pH, so I just plugged that in.
Okay. So I think if we do, I think if we do C is close to that pH. Well, let's just try doing C and see what happens. So the titration we're doing here is we've got a 50 milliliter sample at 0.04 molarity. The Ka equal to 1.4 times 10 to the minus 4. Turns out it's lactic acid.
If you did want to do D, though, the pH is 4.031.
Let's do D. We'll do D. So we're going to add 7.5 milliliters of 0.16 molar KOH. This is doing part D. I'm going to try to fit both the reaction and the equilibrium table onto one board. I hope I don't squeeze myself out. We'll see. So the first thing we want to do is we want to look at the reaction. I'm going to be reacting again, taking my shortcut and just calling it LAC. That's the lactate anion.
Really quick, where do we get the 7.5 milliliters?
Because we're doing part D.
Oh, okay.
Part D is specifically doing 7.5 milliliters. We could apply the same logic to pretty much any step in the process, just changing how much we're adding.
Okay.
So we're going to have our lactic acid is going to be 50 times 0.04. Our lactic acid, our hydroxide is going to be 7.5 times 0.16. I'm going to leave this in millimolar because I like millimolar. We will have 2 millimoles of lactic acid. And we'll have 1.2 millimoles of hydroxide. Starting with zeros here. Again, this was a mistake that a couple people made on the midterm. Whenever we're talking about these acid-base reactions, we almost always do it one proton at a time. We just add one proton, right? This situation, we can only add one proton, but if we were looking at polyprotic systems, we still do it just one proton at a time. Since it's a 1-to-1 ratio, we can clearly see the hydroxide is limiting. So I'm going to have minus 1.2, minus 1.2, plus 1.2, plus 1.2. I'm going to have 0.8 left over, 0 left over, 1.2. I don't really care about water. The only thing that's important is I have 1.2 made. Now, I want you to notice something. Think back to problem 18. Do we actually need to do the ice table to solve from here? We've got weak acid, we've got conjugate base. Do you see what's coming already?
Oh, the nine something Hasselbalch.
Yeah, the Henderson. Yeah. Yeah. If you can't remember the Henderson-Hasselbalch, we know we're going to get to, I'm going to put it down here at the bottom because we know we're going to get to Ka equals concentration of conjugate base over concentration of weak acid times H3O plus. We know we're going to get to that. let's see how we get to that. Because we've got weak acid and conjugate base both present, we get to pick which one is going to interact with water. Technically, both do, and they're going to establish some equilibrium, but we get to pick whether we're looking at the H3O plus equilibrium or the OH minus equilibrium, because we've got both present. There are situations like initial pH, when we don't have both present, we don't get to pick. At the equivalence point, we don't have both present, we don't get to pick. In the buffer region, we get to pick. So let's go ahead and pick the easier one, which is going to be HLAC with H2O going to H3O plus LAC minus. I'm almost already bored of doing this table, and it's not even lecture yet. This is like all we're doing today. 0.8 divided by the total volume, which is going to be 57.5. Notice since I left it in millimoles, I can leave it in milliliters and be okay, right? Because that's 0.8 millimoles divided by 57.5 milliliters. The millis cancel out. That H3O plus is 0. And my lactic acid here is going to be, my lactic anion is 1.2 divided by 57.5. I'm going to leave those as fractions to show you something else cool that happens. Again, we're getting a little bit ahead, but this all just comes out from practice and doing it over and over again. My change is going to be minus x plus x plus x. If I'm using the x is small approximation, I've got 0.8 divided by 57.5. That's the 7.5 plus the 50. I have x, and I'm going to have 1.2 divided by 57.5. I'm then going to set up this exact thing that I knew was coming. I'm going to have my Ka, 1.4 times 10 to the minus 4, is equal to 0.8 divided by 57.5 divided by 1.2 divided by 57.5 times x. Notice what happens in this situation.
Why is it not products of reactions?
Oh, because I totally made a mistake.
Okay.
Because I totally made a mistake. The 0.8 should be on bottom. The 1.2 should be on top. Thank you. 0.8 should be on bottom. 1.2 should be on top because it is still products of a reactants. The reason I left that total volume there is because notice if we're doing everything in like one beaker, they both have the same total volume. So as long as I'm taking a ratio of molarities, the total volume cancels out. And I could just do a ratio of the moles. This gives us an even greater step of, oh, we can just ignore the equilibrium table. As long as they have the same total volume, we can just do a ratio of moles. And then it becomes really easy to solve for x. Now, we can solve for x. We can get our pH. We're going to do 1.4 times 10 to the minus 4 times 0.8 divided by 1.2. Take the negative log of whatever that is. What do we get for the pH? 4 something? Should be 4 something.
Exactly. It comes from a relatively strong acid. Because what you're thinking about is
I'll do it too.
but it's stronger. So,
What'd you get?
Yeah.
4.02.
That's what I was expecting. Can I see? Negative log of that should be 2.03. You forgot your decimal point. That's all. You did it all right. You just forgot your decimal point. Now we should have. You should have an eye for seeing like if we've got something that's on the order of 10 to the minus 5. It should be the negative log should be on the order of 4. So there we got a pH of 4. Now to get to problem J, the tricky one.
I just went through it and maybe my basic approach to solve for something, but I got an answer that does not make sense. So
What answer did you get?
1.4 times 10 to the negative 4.
1.4 times 10 to the minus 4. It looks like you just got the Ka back. So you canceled something out and just got the Ka back. So let's think about what we need to do for problem J. I'm going to try to leave some of this work up. And we're going to take some of this work down. Right? So we're going to try to do this whole process backwards now. I'm going to change a few things. Problem J. We're trying to get to a pH of
3.22.
So right away, we know it should be less than 7.5 milliliters. No, 10 to the minus 4th still doesn't make sense. We know it should be less than 7.5 milliliters because 7.5 milliliters already put us past that pH. If we did the other problems, if we did B and C, we could probably even narrow it down to a particular range. It's probably someplace between 2.5 and 7.5 milliliters. If we did C, we would have even more information, but we know it's probably someplace in that range. So our HLAC is actually going to have the same start. 50 times 0.04 gives us 2 millimoles. And then I like the way you set this up. You have Y times 0.16 gives us Y times 0.16 millimoles. This is still going to be the limiting reactant. So I'm going to have minus Y. Let's just call this minus 0.16Y. This will be minus 0.16Y and plus 0.16Y. 2 minus 0.16Y, 0, and 0 plus 0.16Y. Now, we already know where we're getting to, right? So if we set up the ICE table, we know at equilibrium, this is going to be, using the extra small approximation, HLAC initial still. We know the lactic acid is going to be the lactic acid concentration initial still. And we know the pH. So we know the H3O plus concentration. If we do 10 to the power of negative 3.22.
You want this number 5?
Yeah.
We get 6.02 times 10 to the minus 4. And again, we kind of see the train coming, right? We've seen what happens. We know that we have a minus x plus x plus x. We know that the x is essentially this value. But when we put these two things together, so essentially whatever number we have here, we're going to use the extra small approximation. Whatever number we have here, we're going to have the extra small approximation. Here we have 0 plus x. So we know that this is the H3O plus all comes from this equilibrium. Now that by itself doesn't help us out, but notice we still end up with the same kind of setup. Because we can use the extra small approximation, we're going to end up with this setup. I'm going to give myself a little bit more space for this setup. We're going to end up with this setup where we'll have Ka is equal to products over reactants. So we're going to have the lactic. We're going to have 0.16Y divided by, I'm just going to call it total volume. Let's call it V total. Divided by 2 minus 0.16y divided by volume total times 6.02 times 10 to the minus 4. We can plug in the Ka as well, 1.4 times 10 to the minus 4. Now, does it actually matter what the total volume is going to end up being? No. Right? It's going to matter because it's going to give us a number of moles, but because, again, we're taking a ratio of molarities, that total volume is going to cancel out. It'll give us one less variable to solve for. Because technically we should plug in that total volume is equal to 50 plus y, but the 50 plus y is still going to cancel out of that fraction. That'll make our lives a little bit easier. I can just erase that. I can just erase that. And now we can just do algebra. Right? I'm going to have, let's do this. 2 minus 1.6y is equal to 0.16y times 6.02 times 10 to the minus 4. That's my H3O plus concentration divided by 1.4 times 10 to the minus 4, my Ka. Can you do the algebra from there? Now, what I just did was not trivial, right? The process of doing titrations takes practice. That's part of why I gave you so many problems where you just have to keep calculating these points. Keep calculating these points. The tricks that I showed you in doing the last two problems really just comes out of the fact that I've done this so much. I know the tricks. My hope in giving you so much practice is that you would develop some of these tricks on your own, that you would see it, you'd get sick of doing the same thing over and over again, you'd recognize the patterns and start to make your own shortcuts. That's the hope. So, at this point, we should be able to solve for y. Once we solve for y, hopefully we'll get a realistic volume. Notice, because of the ratio of our H3O plus concentration to our Ka, we should get things that are on the order of whole numbers. See ya. Oh, that's a little bit lower than I was expecting. What number did you get?
I got 2.35.
That's what I got. Okay. So I got 2.35. So
what does that number mean now?
Oh, great question. What the heck did we just solve for? What is y?
Oh, is OH minus?
Which part of OH minus?
What is it? Oh, volume.
Volume, right? So if we follow back, since we did this problem backwards, if we start down at the H3O plus concentration, we follow back to the first place we run into y. This is it, right? Our first step is y times 0.16. That's volume times concentration. So once we do volume times concentration, we know that we're doing volume is what we're looking for.
That makes sense.
Cool.
Thank you.
Sorry. Since a couple of you are leaving, I think I'm going to stop the live thing. Hopefully that's good enough for all of you. Start showing up to office hours if you want more of this.